This is a review of the open-ended questions that showed up at the end of Exam 1 in the fall of 2019. So I'm going to go over both version A and version B questions, but of course they're related. I try to make them analogous. So in question 19, the question asked you to represent an atom, in this case either chlorine or sulfur, in several different ways. And I suggest you have a periodic table out in front of you so that you can kind of follow along as this goes, as we go through this. So chlorine has an atomic number of 17. Sulfur, has an atomic number of 16. So when we're going to write the electron configuration for each one, we need to identify what orbitals are going to be filled up with how many electrons. So for chlorine, we're going to start with 1s2, then go to 2s2, then go to 2p6, then go to 3s2, and then 3p5. That will be sufficient to account for 17 electrons, and we're filling them up in the order in which orbitals fill from low energy to high energy. Sulfur has one fewer electron, so it's going to be 1s2, 2s2, 2p6, 3s2, 3p4. Now for either one of these, you could identify that this first part of this is actually a neon core. So you could also have written neon 3s2, 3p5, or neon 3s2, 3p4. For the second part, I asked for an orbital energy diagram. So an energy diagram shows the orbitals and their energy levels and shows how many electrons are in each orbital. So to draw this, we need to recognize that chlorine starts with 1s at its lowest energy, then 2s, then 2p, then 3s, and 3p. So all I've done so far is I have drawn the energy levels themselves. I also need to indicate that this is an axis of increasing energy. And then finally, I need to show where the electrons are. So 2 electrons in the 1s, 2 in the 2s, 1, 2, 3, 4, 5, 6 in the 2p, 2 in the 3s, and then 1, 2, 3, 4, 5 in the 3p for chlorine. Sulfur is going to be similar, but of course it will have one fewer electron. Here's its basic energy diagram, the energy levels. If we put 2 electrons in 1s, 2 in 2s, 1, 2, 4, 5, 6 in the 2p, 2 in the 3s, and in this case we're going to do 1, 2, 3, 4 electrons in the 3p subshell of sulfur. So finally, the question asked for the shell model for either chlorine or sulfur. And it is the case that you have to know all the pieces that need to be present for a shell model. So the first thing that a shell model needs to show is the nuclear charge. So for chlorine, that's going to be 17. For sulfur, it's 16. So we need to be able to show how many protons are attracting the electrons in this system. The second thing is the shell model shows every shell. So we can see from what we've drawn up here and here that chlorine and sulfur both have electrons in 3 shells. So I've drawn those 3 shells, and for chlorine there's going to be 2 electrons in the first shell. That's right here. There's going to be 8 electrons in the second shell. 1, 2, 3, 4, 5, 6, 7, 8. This is the second shell. And then there are going to be 7 electrons. 1, 2, 3, 4, 5, 6, 7 in the third shell. Sulfur is going to be similar, only it's going to have one fewer electron. And that's what it looks like. In most cases where people missed things in this problem is sometimes people did not know exactly how to order the orbitals in the orbital energy diagram. So the energy levels here. Lots of people didn't actually label that this is an energy axis, and that's just an important part of the problem. And a lot of people drew versions of some sort of core model when what I asked for was a shell model. One of the things that you're going to want to be sure that you do is to make sure that you know what the terminology is so that when something is asked for on an exam, you're able to pull that out. And that just takes practice, doing different kinds of problems and making sure you're familiar with the language. Okay, so I'm going to go over question 20 from version A. If you have version B, you can zoom ahead because I'm going to go over version B separately. So this question is about a compound called magnesium nitrate. The first part of the question is, what is the molar mass of magnesium nitrate? And the first thing you need to know about that is that the molar mass, by definition, is what is the mass if I have 1 mole of this compound. If I have a whole mole of this compound, then I have 1 mole of magnesium. I also have 2 moles of nitrogen, and I have 6 moles of oxygen. Now, in order to get to that, you had to know how to interpret the subscripts here, and there were a few people that are still figuring that part out. Once we know that this is how many moles of each element we have in a mole of the compound, then we can figure out what is the mass of each one of those using the molar masses of the elements. So we know that for magnesium, it has a mass of 24.30 grams per mole. So that means it's going to contribute 24.30 grams to our 1 mole sample. 2 moles of nitrogen, each one is 14.01 grams per mole. And again, these are numbers we got from the periodic table. So that's 28.02 grams. And 6 moles of oxygen at 16.00 grams per mole. And if we add all that together, we get 148.32 grams. And this is really 148.32 grams per mole of our magnesium nitrate. So that's its molar mass. There were a number of students who ended up assigning these units as AMUs. And it is true that this numerical value would be what you would get if you were doing, let me just write it up here, 148.32 AMUs per molecule. And this is a true statement. 1 molecule would have a mass of 148.32, but because I asked for the molar mass, I really wanted what is the mass of a whole mole of this stuff, and that's going to be in grams. Okay, our next question says, if we have a 358 gram sample of magnesium nitrate, how many moles do we have? Before we even do this problem, let's figure out what we already know. So we know that 1 mole has a mass of about 150 grams. So we know this is going to have to be more like 2 or 2.5 moles, because in order to be 358 grams, we're going to have more than a mole. How do we set this up? This is a situation where we're given a sample. So we're always going to start with the sample as given. So 358 grams. Because what this problem is actually asking us to do is say, don't change the sample, just change how we describe it. Instead of describing it in grams, we want to describe it in moles. And so the question we have to ask ourselves is, after we're starting with the 358 grams, do we have a relationship that allows us to go from grams to moles? And the answer is we do. That's in the molar mass. And so if we arrange the molar mass properly, 148.32 grams per mole. And I'm going to write moles of magnesium nitrate here, and you'll see why that's important later. And so if I do the math then, what I get is 2.4137. I'm going to be limited to 3 sig figs, so I'm going to get 2.41 moles of magnesium nitrate. It's important here to say what kind of moles we've got. What is it that we're counting? Are we counting the unicorns? Or are we counting the unicorn's legs? Is one way to think about this. So in this case, we're counting the whole thing. And as we predicted, it was going to be somewhere a little more than 2 moles in the sample to have a mass of 358. Now the last part of the question asks, how many total atoms are present? Let's note that what we have right here is a counting of the compound. So we can start from here and figure out how do we get to counting of atoms. So let's start with what we've got, 2.41. And I just did it with all of the in sig figs here too, but you didn't have to do it that way. 2.4137 moles of magnesium nitrate. Well, let's start by converting this to molecules of magnesium nitrate, because at some point we need to get to some total atoms. So we know that for every 1 mole of magnesium nitrate, there are 6.022 times 10 to the 23rd magnesium nitrate, what we're going to call molecules. It's kind of messy, but you've got the gist. And so this is going to allow us to cancel out moles of magnesium nitrate. Now we've got molecules of magnesium nitrate. Now what we want to get is total atoms. So the next conversion factor we're going to need, and I'm kind of going to have to put it down here, is how many atoms are in a molecule of magnesium nitrate. Well, what we can see is that 1 molecule has a magnesium, that would be the first atom, 2 nitrogens, so now we're up to 3, and 6 oxygens, so that's a total of 9 atoms. And if we do that, so that's going to allow us to cancel the magnesium nitrate molecules within magnesium nitrate molecules. And that's going to allow us to calculate 1.3081 times 10 to the 25th atoms. And we're going to be limited to 3 sig figs, so that's going to be 1.31 times 10 to the 25th atoms. A very common mistake that people made was to get this far, but just to label this as atoms, as though there's this many atoms in a mole of this compound. And it is true that there's this many atoms if you have a mole of atoms, but this is not a mole of atoms, it's a mole of the compound. So I encourage you to go back and look at this some more. And if you're still exploring and trying to better understand these kinds of conversion factor problems, come in and get some help with them. Okay, here's the solution for version B. In this case, we're talking about calcium nitrate, and the first question is, what is the molar mass of calcium nitrate? And the first thing we have to recognize is, what is the definition of molar mass? This is the mass that we would have if we have a mole of the compound, not just a single molecule, but a whole mole. And if we have a whole mole, that means we have 1 mole of calcium. It means we have 2 moles of nitrogen. And it means we have 4 moles of oxygen. One of the things to recognize is this requires that you carefully count out how many of each atom you have. And if you need some help to make sure you know how to do that, when you've got parentheses and things, come in and get some help. So this now gives us how many moles of each of the elements that are contributing. Now we need to figure out what is the mass that calcium, nitrogen, and oxygen are contributing so that we can add it up to get the total mass of our mole of calcium nitrate. So we know that for calcium, the molar mass for the element is 40.08 grams per mole. So that's going to contribute a total of 40.08 grams from the calcium. We know that for each nitrogen, there's 14.01 grams per mole. So that's going to contribute a total of 28.02 grams for the nitrogen. And we know that the oxygen is 16 grams per mole. So each of these numbers we're getting from the periodic table. And that's a total contribution of 64.00 grams from the oxygen. Now if we add all that up, I'm going to write it over here, what I get is 132.10 grams. And because by definition we started with the idea of this being a mole, that means it's 132.10 grams per 1 mole of calcium nitrate. One of the very common things that we saw when we were grading the exam is that people did the calculation right, but then wrote 132.10 AMUs. Now you can do that if what you're counting is a molecule of calcium nitrate. So remember that an AMU is a very small mass unit, and this is what the mass would be if you have a single molecule of calcium nitrate. But if I want a whole mole, which is what I wanted in this case, then the units that I'm going to attach to those numbers are going to be in grams. So the next part of our question is we've got a 795 gram sample of calcium nitrate. We want to know how many moles of calcium nitrate we have. So this is a situation where we're given a sample, and we're not going to change the sample, we're just going to change how we've described it. So we're starting with our 795 grams. And we want to say, is there a relationship between grams and moles that would allow us to just describe this sample, instead of in mass, in terms of moles? And of course we do have such a relationship here. So I can use the molar mass, 132.10 grams, in 1 mole of, calcium nitrate. No, calcium nitrate, sorry, I keep saying that wrong. And of course that allows my grams to cancel. And I can, my final answer here, which is let me write it in black, hold on. 6.0181 moles, and I'm going to be limited to 3 sig figs, so I'm going to say 6.02 moles, and let's say what kind of moles we're dealing with here. This is calcium nitrite, NO2. It's important to make sure we're tracking what are we counting. Right now what we're counting is moles of calcium nitrite. Now that counting is going to come into play in an important way in the final part of this problem. In that same sample, so again we're starting with the same sample, how many total atoms are present? Let's start with how many moles of the compound that we have. We know we have 6.0181 moles of calcium nitrate. Let's convert that to molecules, and the reason I think that's a good first step is because we eventually want to get to atoms, and so it's much easier to get from molecules to atoms than to get from moles to atoms. This is not the only way to do it, but this is a good start. So let's convert moles of calcium nitrate to molecules of calcium nitrate. And I'm going to do that using Avogadro's number. So I know that in 1 mole of calcium nitrate, there are 6.022 times 10 to the 23rd molecules of calcium nitrite. That's going to allow my moles of calcium nitrite to cancel. It's going to give me molecules of calcium nitrate. And now what I can recognize is that in a single molecule, I'm going to have 1 calcium, 2 nitrogens, and 4 oxygens. So I'm going to have 7 atoms in 1 molecule of calcium nitrite. And that's going to allow my molecules to cancel. And it's going to give me a final answer of 2.5369 times 10 to the 25th, which to the right number of sig figs is going to be 2.54 times 10 to the 25th atoms. And this is all the atoms, atoms of calcium, nitrogen, and oxygen. One of the things that we saw a lot of when we were grading is a mole of calcium nitrate being converted to 6.02 times 10 to the 23rd atoms. This is where it's important to make sure you know what you're counting. So people sometimes did this, attached the word atoms here, and thought they were done. It was a good first step. It didn't go all the way. And I think with some more practice, you'll get it. If you are having difficulty with figuring these kinds of conversion factor problems out, come in and get some help. We can do some more practice together. Okay, so here's the final question. I'm going to answer it for version A. The version B question in this particular case was exactly the same. It's just that the pictures were swapped. So you just have to separate out and substitute which state is the right answer. So the question asks, so we've got 2 pictures here. It's a single ion in 2 different states. So this is one ion that can be in either one of these configurations. And what we see is that in one case, its electron is in the n = 3 shell, and in the other case, it's in an n = 1 shell. Some people noted that this is the ground state and this is an excited state, and that is true for this ion. The question asked us to say in which state, A or B, is the electron more stable. And most people were able to say for this version, state B is more stable. And the question is why? And what a lot of people said is B is more stable because the electron is closer to the nucleus. And if you said something like this, and sometimes people said it several different times in several different ways, but if this is essentially what you said, this was worth about 2 of the 4 points. To get the other 2 points, you had to add a little bit more to your explanation. You had to say something like, Coulomb's law, and I'm just going to abbreviate it here, Coulomb's law indicates there are 2 factors to stability. And that would be charge acting on the electron and the distance between the charges. Further, you would have to say, in this case, the charges are the same. In other words, +2 in the nucleus interacting with -1 on the electron. So it is distance that matters. So that would be the kind of thinking or the kind of explanation that would get full credit. Let's talk about the answer to B. I asked for what the symbol for this ion was. And let's just think about how we identify what chemical symbol to write is. So you'll remember, going back to the very first day of class, the thing that defines the element is the atomic number. And the atomic number is equal to the number of protons. In this particular case, the nucleus, we can see, has 2 protons. And if the atomic number is 2, then by definition, we must have a helium particle. Now, normally, helium would have 2 electrons in its shell, somewhere in its shell, to be neutral. In this particular case, we only have 1 electron, so this must be a helium plus ion. So to get full credit, you had to have all of this information. Some people also tried to write a mass number, but in order to write a mass number, we would need to know how many neutrons are in the nucleus, and we don't have any information about that. So if people have questions about how this explanation works, come and talk to me.